Thank you. I would not have seen that. I was looking for a round button, not a square thing, because we're taught
same thing
that
last time.
Yeah. Well, I'll forget it again next time.
Yeah.
Hello, YouTube. Yes,
Hello.
we both. Well, I hate computers. Do you hate computers, Ben?
I have a. Now we're live for sure.
Yeah, you're too young to fully hate them yet.
I'm gonna mute that, but we're live, so I'm gonna chat as well. Hey everyone. Yeah, I didn't finish my LinkedIn post. Let me do that real quick. What were our topics this week, Bill? I've got logic, family, evolution, clean all nets, quirks.
Oh, I want to talk a little bit of design for manufacturing. Oh, we want to talk about how to make your own Asic chip. We've been asked about chip layers and stuff. We're going to talk about that. We're going to talk about families. We talked about, advanced Schottky parts and the history of parts. So the list is long enough that we won't run out of topics before we're done. So unfortunately, my chat widget is not showing up.
I can see the chat.
All right.
On my side, but I get it. In XSplit, your chat widget's not showing. So I'll just keep an eye on the chat over here.
Okay. Very good.
And welcome, Wes, Chris. There's a few others. Please feel free to ask us anything. And Bill, you're obviously there too on chat.
Yeah, I just found it.
So what are we starting
with today? I love computers.
What are we starting with today? Last week, we actually touched on the evolution of logic families and how a lot of people sort of have, professional engineers still learn about it in school. And I guess even if you're doing an associate, about still the same old thing, what's the difference between TTL and CMOS? But there's a lot more than just TTL and CMOS.
Well, basically, I was talking about everything CMOS-y and layers and everything. And so I actually show a wafer. There's an old wafer. That's a 5.5-inch wafer. The wafers these days are like dinner plates. So that's kind of a, well, for yield, if you're going to do 28 steps, including photo etch, photo resist, washing it away, exposure, running x-rays, you might as well do it to the biggest piece of something that you can afford to produce. So. Ingot.
A huge chunk of silicon that's grown as a single
It's
crystal.
grown, that's right. And the silicon wafers actually have an edge that tell you the orientation. Hold on a second.
So where did you get these anyway? And is it
Commodore?
How can...
One I got from the basement of MOS years later, but this we used to throw these like frisbees, and they shatter like glass. But if you look,
I was going to say, isn't that dangerous?
But there's a flat edge here. I don't know if you can see it.
Yeah,
but
it's machined flat on that side of the ingot.
Right.
Yeah.
But it coincides with the crystal lattice. So that flat edge tells you the orientation of the crystal lattice, which is really important when you go to scribe these things. And by scribing, we do it just like glass. It's just kind of just like it sounds.
That's for separating each
the die,
dice.
Right, from the wafer.
Okay.
And again, these shatter. Back when I had long hair, I'd throw one, it'd shatter, and I'd be shaking glass out of my hair for the rest. I'd look like a shaggy dog shaking glass out of my hair. Yeah. So, hey, here's going back to this. I was just having a conversation the other day with the difference between BJTs and JFETs. Oh, that's a junction FET. Actually, in real life, CMOS FETs don't have a junction. They have an insulator right here. So but the principle's the same. One is a current device and one is a voltage device. unless it's switching, then it's a current device because it's charging all the capacitances around it, including the load. Here we go. Here are two MOSFETs that show the insulation in the diagram. And one will pinch off, that's depletion mode. It's like a switch. It's actually more like a vacuum tube than any other device we use today. And one will pinch off and the other one will start pinched off and will actually become a conductor with the application of gate voltage. So, and this is what makes up everything. You build your inverters with two of these. And in CMOS, there's actually only a NAND gate, a NOR gate, an exclusive NOR gate, an inverter, and a pass device. That's it. That's right. That's right. Ooh, here's the SCR effect. We don't see this much, but in the old days, there's two transistors back to back form a silicon controlled rectifier, and they would kick on, and you would have to power off the part to undo the SCR latch up, it was called. So
power applications like motor drives.
Yeah, absolutely.
And there's some you can buy. They're like pucks. They're really big.
Yes, they are.
Silicon, and they cost maybe $700 to $1,000 a piece.
There's probably ones that have an inlet and outlet for liquid cooling.
Yeah, and you don't want to blow those things up there.
No, and probably hurt you.
Machines, because you need a huge current handling capacity for the spot welding. So they use these giant thyristors or SCRs and a capacitor discharge system.
Right. And then SCRs are rectifiers, so they have the back-to-back ones, and they call them thyristors in the old days. I don't know what they call them nowadays. But they have a single gate, but they'll conduct in both directions. And that's what's in your lamp dimmers at home. So, hey, here's the family, though. Let me show it real quick. Boink. And this is what we were talking about last week. We talked about how things started with Schottky a little bit. And Schottky is just horrible to work with. It is noisy, noisy in radiation. It's noisy on the lines themselves. And it's hot, and it uses a lot of current. So I joined electronics right as we were going to LS parts. And we were in heaven, and then they all stopped being available for about a year when the Game Boy came out. They literally were building Game Boys with LS parts instead of CMOS parts. And, there we go. And, so you couldn't get any for like 6 months around Christmas one year.
That's like capacitors 2 years ago. And
DRAMs
2 years to a year ago. And DRAMs,
a couple times.
They all got dried up.
Do you remember when the resin plant, the Kyocera's resin plant caught fire, and nobody could make chips anywhere for a couple months because it turns out everybody used the same resin plant in the world, right?
No one thought that through, or put.
Yeah,
that's the unfortunate. Actually, that's a really interesting point. That's the unfortunate result of people hiding their supply chain information for competitive reasons. Right. Nobody tells anyone else who any of their suppliers are, and you don't want to because that's part of your trade secret. Unfortunately, yes, it means eventually if there's some unique product that's a playing field leveler, let's say that imagine there was only one PCB factory in the whole world when PCBs were brand new, and everyone else was still doing hand-soldered point-to-point wiring. And suddenly, just to stay in business, you had to go start using PCBs because your production costs would drop significantly, and your competitor was already using PCBs, so you had to start because you didn't want to be pushed out of the business. Suddenly, everyone's using PCBs, but there's only one factory. That's a problem.
Right.
And so I'm actually grateful for governments, particularly the US government, demanding that there are alternate sources because, for military contractors and things, because without that, if it was all pure, now I'm normally pretty conservatively minded, but without a government to step in and say no, there has to be additional sources,
critical
at least for us as a customer, we demand multiple sources. But what it means is it maintains healthy competition and it prevents supply chain bottlenecks. That's really important. So I'm grateful for that. Yeah.
So looking back at this, remember the CD 4000 series?
Yeah, those were awful.
They were hard to use.
It had some good advantages though, if you wanted something that didn't have to be fast but operated at high voltage. So a lot of guitar pedals use 4000 series CMOS chips because you can run them all off the same 9-volt battery as the op amps. So that's a classic use case for those that
5 to 15 volts. Yep.
They don't have to be fast. You're not running crazy fast, and you can have an analog bilateral switch gating
CD
an
4016
or something.
Yeah,
exactly that one, or a 4066.
Oh, and they're the phase lock loop. Yeah,
those I have this marvelous delay effects unit that's a classic from the 80s. They're still fairly sought after, even as used old units, and people still service.
They still sound good.
They sound amazing, and they do 12-bit A to D and D to A, but to get the dynamic range that's necessary for good quality audio, they did this trick. They used analog companders, so they compress the audio signal going in and expand it coming out. And those engineers, I'll tell you what, they were real good engineers who designed that hardware. Because they had all sorts of crazy switching and digital and analog all on one huge board. And they have sample and hold. They used the 4066 as
quad
a
bilateral switch. Yeah, that's a second form of the quad.
And that goes into an LM311 high-speed comparator. And they have an R2R, a 12-bit R2R ladder
for DA,
and a custom Asic that took care of the successive approximation process. And it took care of storing the audio data stream into a DRAM bank and took care of DRAM refresh, all in one big custom ASIC.
So it was a 1-bit D to A converter, basically, that could still it could still produce all the information, but
well, it was 12-bit quantization because they had that in the successive approximation loop. The digital part of the SAR was done inside, and I don't know. Could you bring up a successive approximation?
I did a thing on Hackaday on it.
So yes, it would. In a sense, it was 1-bit in that it had the high-low output of the comparator, but digitally it would be shifting that into the successive approximation shift register, and that would give you the full 12 bits. But to get high-quality audio, and these things are amazing, they actually have full 20 kilohertz, 20 hertz to 20 kilohertz bandwidth, and over 90 dB dynamic range, which is impossible to do in 12 bits mathematically. The only way they did it was because they used the analog comparator circuit in front of it, they used the compander. They used the compressor in the front and an expander in the back, and they did very, very, very careful analog circuit and PCB layout. The board's only 2 layers, so they don't have ground planes everywhere. They had to be super careful to not have problems with noise. And the units, it just sounds amazing, and it's very low noise.
Sounds fat, probably. The old stuff had little stuff that pleased the ear, and you may not even know where it came from, is my experience. Especially distortion and tube equipment. Yeah. So here's a 1-bit comparator used to make a delta sigma modulator, and I actually showed it on the scope, where the scope would do the actual averaging, and you could see the signal out of a single bit comparator. So, and I forgot everything that's in this article, so I'd have to read it again. But and I talk about successive approximation and everything else.
The cool thing about delta sigma process is you can use it for A to D and D to A, like you can with successive approximation. You can kill two birds with one stone.
And do digital filtering. Yeah.
And there was a white paper put out some time ago by Xilinx, how to build a delta sigma D to A converter just in VHDL.
Right.
And you take up one pin on your CPLD or FPGA, and you've got a high fidelity analog output. All you need is a low pass filter, and then any other kind of amplification that you might want after that. And you've got a really high quality analog output that'll go from DC to probably 1/100th of your main clock frequency going into it.
Right.
So it's a pretty useful technique if you have programmable logic as well.
In one of the other articles, I talk about the math that you just spoke about, how 8 bits actually comes out to be about 63 dB signal to noise, somewhere in there. And by the time you get to 9 and 10 bits, you get to around 80 dB, which is the limit of a lot of analog amplifiers. So people that go, oh, I have a 24-bit system. Yeah, but only the bottom 11, 12 bits are useful.
Yeah,
so
it's often the case. Yeah.
And the companding you were talking about, there's companders for VoIP. That's big these days. And like micro law. And it's based on the human ear. We hear it's really articulate on fast moving part of the signal, but then where the signal slows down, it's not as accurate. And so it feeds the ear what it wants to hear.
Yep.
So.
Yeah.
So I knew a guy that used a CD4000, and he did something really interesting with it. He put it down an oil well, right? And the problem is the temperature in the oil well is a couple hundred degrees. So TTL LS couldn't do it, right?
Yeah.
But if you derate the speed of CMOS still works. It slows down with heat. And so he's running like a 1 kilohertz clock, and it's working at like 200, 250 degrees Fahrenheit. So
that's crazy.
Yeah, that's 100 some degrees for you Celsius people. So, yeah, they have their time and place. My favorite phase lock loop is the CD4000. It's like the 4060 or something like that.
So something that became an issue with all these different families, and is still an issue everyone has today. Firstly, that
yeah, sort of. Right. Because you're from south of the equator. Linear time. Yeah. Right. So, okay.
You have a well-known story about the C128 and signal integrity. Maybe you could share that in a bit, but something that's constantly caught people out is these chip manufacturers will upgrade something to some new semiconductor process, and then
I've heard this. Yeah,
they say that the chip they don't change. They may revise the data sheet a little bit because some of the numbers in some of the tables will change, but the part number doesn't change. And you could be ordering that part, and then suddenly your product stops working or becomes unreliable, or you no longer pass
FCC,
EMC testing.
VDE. Yep.
Yeah. So could you shed some light on what's going on there?
Well, chip designers always think faster is better, right? And to the point where a data sheet doesn't list the minimum speed of a gate. It just doesn't unless you get a special kind of part. And so don't ever use a part for a delay, because by the time you route to an ACT part or something, and it's got a 1 nanosecond delay or something, by the time the routing and everything's taken into effect, you may create a delay of minus 0.5 nanosecond.
Well, as far as phase is concerned, right?
Yeah, as far as getting through it, right. So faster is always better. So a chip designer doesn't think anything about making a chip faster without telling you. Now, in tri-state buses, we have to do a dance where we go, get on the bus, but not too fast. Now go away, but you get on the bus, but not too fast. And we have to do this dance. So we don't get contention. When the current contends, I can't do it with that finger. When the old and the new each are trying to sync into the bus, you get these huge currents, and these huge currents radiate. So the more contention you have, the hotter things get, but also the more FCC radiation you get. So especially when they're hard buses where he's going, I'm on too fast.
Well, give us an example of that. So if you had a bus like PC, so it's different again. It's different again with this is why we moved to PCIe and other architectures in modern computers where it's more or less like a bunch of channels of Ethernet, and they're all switched by a chip that aggregates and controls the traffic, right? So there's no contention, but many designs, particularly in industrial electronics, we're still using basic buses and things like that, like I2C, SM bus, SPI,
or data buses and address buses in a computer.
Exactly, just simple, functional. Why change it if it's all you need and it doesn't work, and it works, right? But then what you're talking about is if you have multiple masters and they're contending over it,
right.
Or multiple slaves that want to send out an assertion to say, hey, I need to do something here, like an interrupt.
Yes, and it turns out that especially with some of the CMOS parts, it takes a long time to tri-state. They come active fast, but they don't go away very fast, and so you get a lot of contention that way. After a while, you learn to just make two signals, one to tell him to get off the bus, and a known time later you say, now you can get on the bus. And that's how we had to fix it.
So what was the problem you had with the 128 though? Because you, at the 11th hour, were trying to get these things to production, but they did not pass EMI. What was the cause?
No, that's not what the problem was, actually. We had made our CES show, and we had one rev of the PC board to go into production. This was it. This was going to be made at times a million, so it'd have to work. And on the last rev of this 2-layer board, and it took us a full day to route the last 8 traces of this board, a full day just to lay in 8 traces. And so we get the boards back, and 20% of the units won't run the Z80 processor correctly. They only run the 6502 perfectly. The Z80, 20% of the time, it'd crap out.
So
and it's a multiple bus master. Yeah.
Just for those who aren't familiar, because I did use a 128 for a short while.
I used one for a doorstop. Yeah.
The key differentiator between the C128 and the C64 was that it had an additional processor, which was the Zilog Z80.
Yep.
And it could dual boot Commodore software, and it was fully C64 compatible, plus with a few extra features. Or you could reboot and go into CPM, which was the desktop operating system of the day before Microsoft DOS.
And that's what was failing to load. Yeah, CPM wouldn't load on 20% of the units. So I got lucky. Me and my boss, he threatened to fire me. The full story, if I go into it, is I was tired. I was worn out. My boss came in and grumbled about something, and we came to the conclusion he should get somebody else to fix the problem, and I take the week off. So I went home, I had sex, I took a shower, I took naps, and I come back in on Friday, and my boss comes into my office and he says, "Fix it or you're fired." And I'm like, "Good, I want to fix it." I go to the lab, and I got lucky because within an hour I found the problem, and I found it by looking in the old analog oscilloscope, and I would stare into it through this hood, and then I would look up at a white wall and I would see the reverse image, and I could see a glitch in that image. And it was real. I had somebody else do it.
He's going, amazing trick.
"Look at the glitch." And everybody else is going, yeah.
That's worth repeating.
Yeah. So what the problem was is the bus, it was good between the 6502 and the DRAM, but the Z80 was trying to insert itself, and instead of driving it nicely like this, it was going,
like
it's driving the middle. It's like blowing a flute in the middle instead of from the end, right? And so what I did was I added a wire, so instead of reflecting off of it, it kept going. I made the wire go around to the beginning, so now it's a ring. There's no reflections. I mean, there's interferences and stuff, but I removed the stub.
Bits. It wasn't the whole thing, right? It was just one of the bits that was doing
A10, address line 10. And the reason we didn't rev the PC board, this is a packed 2-layer board. There's no room on it whatsoever between here and here. All of the data that goes through there, there's no more room.
Yeah.
And I forgot what I was talking about. What'd you ask? Oh, so the reason I didn't rev the board is I might have just moved the problem to someplace I can't fix with a wire. So I said, the wire I know is better than the problem I don't. And that dang wire that we put on all 7 million C128s cost me like $1 each. I probably spent at least $6 million on that damn wire over the course of the project. But it worked. We didn't have to rev the board.
Out of your salary?
If they would have given me royalties, I would gladly have paid penalties, right?
Yeah, but
I would have taken a penny a unit. I mean,
that's how it goes, isn't it? I mean,
yes, we worked for somebody, and that's it. They paid the money to make the chips and everything. I didn't need the profit. It was just fun to work there,
Yeah. And now, all these years later, you get some notoriety for it, so that's good. It's better than nothing.
Who knew back then, because there was no social network, nobody knew our names, right? Unless we walked in a computer store and we knew how to make the computers put up Easter eggs and stuff.
Hey, Chris is asking an interesting question there. Did you ever abuse that noise or the wire loop to see if you could use it as an antenna for sleuthing people's C128s or seeing what you could pick up from it?
So there used to be a federal specification, and I almost had the name, where you could read a computer from far away by the signals going through, and also CRTs. And it's not lattice, but there's Tempest. There's the Tempest spec that limited how much information you could divine from a computer, like in the next room. And that's for the federal eavesdropping stuff. So, no, I never made a Tempest. There, Chris said Tempest. Yep.
I am going to look up Tempest. It's
important. Cool,
That's
especially an old CRT. You could take the frequency of the CRT that's being modulated and modulate another CRT with some amplification, but you could look at their screen remotely without Tempest.
That's amazing.
So that's the wire story.
I put a pin in my head in something you said. It took you a whole, did you say week or day? To route the last.
Oh, it took a day to route the last 6 to 8 traces. It took us all weekend to route about 30 traces.
Yeah.
It took us 3 days.
So the end of that board, and that's a 2-layer board, 8-bit technology, all through hole, so tons of
DRAMs. Of course, yes.
Given that back in the day, you probably were still taping it up, right?
No, we had just gotten a SiCards, and it took an entire VAX to run, right? So it was like $100,000 workstation. It was $40,000 for the terminal, $20,000 for the card, and like $60,000 for the VAX.
Yeah,
and that's $1980. That's probably $1 million these days.
So that was before the ECAD disruption and revolution of the mid 80s, where I came from, really.
Right. Yeah, we had Mentors and Applicon. Those were the other two that we saw doing PC boards back before PADS and PCAD and all of those guys jumped on.
Well, one of the systems that was mini computer based, I think it was the Applicon, used a light pen. You remember the light pens?
Yes, because you would do swirls and stuff to do commands. It was like editing.
And that's why, to this day, tools like Mentor DX Designer, which I played with a few years back, just an eval, had all these mouse gestures and things, and I could not get used to it. Could not make sense of it. Did not work with any of my paradigms whatsoever. But anyway, I
have a Mentor story.
Quick. I just wanted to latch onto that. You said it took, even with CAD, okay, so this is an important point. It took you a whole weekend. And shoving. Yeah. It took you a whole weekend just to do 32 traces, and the last 8 traces took a whole day.
A whole day.
And people just don't realize, actually, the puzzle that is a printed circuit board design requires time. And even if you're using automation, even if you're using modern computing power, which you should be, to at least in part automate the routing challenge, that last 4% of your design is the slowest. It is the hardest. And there, I've anecdotally collected a number of tricks to speed up the routing process over time, techniques that people use who've got a lot of experience in the industry. But Bill, what do you do on your designs to get that last 6% done or 4% done that seems hard? I mean, does it still take you that long, or are the boards you're working on these days you can pretty much use the tools and get it done quickly?
That's it. I'm a fast turn thing, and I'm in control of the size of the board typically. So to answer your question, if something doesn't fit, I make the board bigger, usually, unless I'm in a housing or something. So somebody said, Chris said, use the auto router to double your time. Good auto routers, they're good. Good auto routers can really save you some time and not trash the board. A bad auto router will trash the board to the point where you can't add that last 6%.
Yeah, and this is why a lot of PCB design professionals say, "Oh, I never use the auto router. I hate auto routers."
It's a tool.
There's 2 reasons for that. One is they get a new CAD package. It's got an auto router, because they all do these days, right? They load a design, they get all their parts placed, and they do the basic rectangle board shape, and they click route, and it does a crap job because
it doesn't know about channels and buses, and
they've spent almost no time setting it up, right?
Right.
Or they just don't like the look of the results. But a practical engineer would use automation, at least in part, because you need to do what you can to get the job done faster. And using the AI and using auto routers can give you an idea of how solvable something is, even just as an experiment. Even if you intend to route it all by hand, you can run an auto router on it with your design rules to see, is this an unrealistic ask, or do I need to modify the layer stack?
Right, which somebody mentioned also, yeah.
Yeah.
Yep, so yes, and I've even done auto place, which really bites, usually. But you can use auto place for arrays, things like that. But I've done auto place just to see if it fits first off and what kind of space I have. But I have done the spreadsheet. And when you do a spreadsheet on how much PC board, I swear I'm within 95% of the time. As to what I can route, at least.
Yeah. So, that's the other point. I mean, I could auto route something where I've got 4 layers, so I've got some unbroken ground planes. I might route all the power and ground first and fan out first, and then just auto out everything else, and then gloss everything up, move a few things here and there, make it look a bit better. But if I can get to 98% doing that, Why spend extra time if you don't need
Right.
to, you know?
Right. Right.
But I
And
agree. A lot of the routing technology out there makes ugly results. But if this thing's going inside a box and it's not going to be noisy, I don't have a problem. No one else is going to see it. I'll know, but
the other
yeah,
problem with auto routers is if you have laid out like a power ground grid first, you have to tell it to leave it alone or it'll go in, remove loops, do things like that. So you want to lay in your foundation, but then you want to tell the auto router to build on top of it, not tear out the foundation.
yeah, and that's another important point. Again, crazy results result because people don't do enough design rules and setup. But there's kind of a balancing act there because you can make your rules so strict that it will never be able to finish,
Right.
or it might get to 60 or 80%, but then you'll do the rest by hand. And what it does, because you're doing the rest by hand, you're going to be pushing and shoving and moving things and rerouting them anyway. So at that point, you might as well just do the job manually.
Right. Hey, so you know about hug and push, right? When on these CAD systems, when we
Yeah,
are moving things, it can actually move things that are movable, vias and the like.
yeah.
I have a problem with hug and push though, and that
What's
is
that?
that it hugs when it doesn't need to. So it'll hug a through hole, for example, like here's the through hole, and then it'll put it here when it had all this room, and when I gloss it, it'll bring it back down close. That's fine, it's within limits, but if you're doing the statistics of production, the further away you can keep your traces from things like through holes, statistically, the less chance you have of a failure. So I wish it had a sort of hug and push.
Yeah, what you want to enable is follow mouse trail,
Oh,
or as you're routing the board, just
just
change. Don't use
that's what
hug
I
and
do.
push. Switch off of hug and push, or use hug and push. See, the reason it does that is that the assumption is you want to maintain as much routing
Room
channel as
as
possible
possible. Right, right,
because presumably you've still got a lot more work to do, and you don't want to be pushing and shoving and using all that compute power to slow down the
right.
process.
Or
If you
or
don't
if you're
have to,
doing low quantity, yeah,
you want to keep room available for future routes.
right,
And if you want it to keep things spread, you just cycle through the modes and use
right,
push and shove, but don't use hug and push,
right,
or use walk around, or
right.
walk around's kind of similar, but and this is the same in Eagle has these different modes, and I guess any PCB CAD worth its salt has this capability, and you can use shortcut keys or mouse gestures interactively to switch and cycle through these different ways of
Yeah,
routing
I
as
learned
you
the
go.
tilde key in Altium, and it shows you the menu that is for routing, and my life changed that day because I could stop trying to remember Control R's and Control D's and stuff. So yeah, it was excellent. Hey,
Hey,
you and me talked
did you
about.
see that? Did you see that Smarter Every Day video where the welders in his shop built a bicycle where they had geared the steering wheel, the handlebars against the front wheel to reverse the steering of the bike? So you would pull the handlebars.
I've seen people try and do reverse steering, and they end up hurting themselves. Yeah.
Yeah, and but a really interesting. I'd suggest looking at that video, because one of the really interesting things that came from that was that he put his 5-year-old son on a bike that had the steering reversed, and within a
He
day
could
he was
learn.
riding it.
Yeah.
He spent 8 weeks.
Plasticity.
Yeah, his brain, like, just proving brain plasticity
Yep.
is there, but it's much more difficult to use in adults.
Which is they can learn second languages quick, music. It's I've lost like all my not that I can play guitar with the number of fingers I have, but I've even forgotten the string names and stuff over time. It's as I get older, I'm forgetting the newest stuff first, right? So I remember a
Yeah.
violin, but I forget my guitar.
Oh, and this was a point that really struck home to me as an ECAD product manager, that people have been using their software for 20 years or 10 years, really know that software, and any change, the learning curve of any change or of things that don't work intuitively the same way, they may work intuitively but not the same way.
Right.
It's just really important to bear in mind, and I wish all software developers would watch that video and realize if like there's a reason why customers get really angry sometimes when you make a change in your software and change the way something works. You can understand why you're forcing them to learn something new, and the older you get and the longer you've done something one way, the harder it is to relearn new things. And that's just a neurological, physiological, scientific fact that we don't get to choose. And it's really, to me, really important. So I didn't understand when I was at Altium and we were killing PCAD, and we wanted people to move from PCAD to Altium Designer, and they all said Altium Designer is horrible. We can't use it. We don't know how to use it. Everything's different. I can't find where things are. The workflow is not the same. And I thought, you're all just crazy. Why can't you just learn? This is actually a much easier tool and much more intuitive and way more powerful and has a lot more capabilities that'll help you. And they're like, no, we're going to pads, because pads at the time was the closest thing to PCAD.
Right. And I didn't like PCAD.
And I just couldn't understand as a young applications engineer in my early 30s even. I didn't know about this brain plasticity issue, right? And I had no what's the word, empathy for these people.
Right.
But I tell you right now, I sure do have empathy for them.
Empathetic as hell now.
Yeah.
It's like my seventh or eighth CAD, and I do have trouble remembering where things are. If I were to mention on Altium, the probably the one thing that I go, oh, somebody could have gotten together on that, is when the command is different in the PCB editor than it is in the schematic editor, and they do the same thing. I would have liked to gone to the same place, under design or something, to find the command. I can't think of any commands that do that right now, but I find them when I'm working.
Yeah.
So, hey, you mentioned the ACT parts getting faster, so I brought up this little guy again. This is the real answer to when ACT parts get faster, and radiation we're talking about, this rising edge gets faster too. So the part not only propagates faster, it does a faster slew rate, faster rise and fall time. And that means the angular frequency, the bandwidth that comes out of its weight, is higher. Not way higher, but higher. So that's what a faster part does, is make a faster edge in addition to a faster latency.
Yeah,
so
and
just
that's why you run into EMI problems.
Yes.
When you may have done nothing wrong, but your semiconductor vendor changes they move to a new fabrication process where there's a die shrink and everything gets faster. Your clock frequency hasn't changed, your firmware hasn't changed, but suddenly things start going haywire.
Right, your edges have changed.
And then you need to do a spin on the board to introduce some
or look at your supply chain again,
or series resistance, or change which chips you're using. Do a lifetime buy of the older version or something.
Especially military, they do lifetime buys. So, here moving forward, let's see if I can bring this up. Here we also have the voltages of the different, back in the day, everything was 5 volts, but we threw away all this green that you see here. This was all margin, right? And we paid to heat the part up, this additional part. So it only made sense to drop our voltage. And now we have a nice symmetrical usage compared to this 2.4 and the rest is garbage here. So, and we see that low voltage TTL, there are some of the 3-volt parts. And as you get faster, you typically get less voltage. And one reason is you simply don't have to slew the voltage as far. You don't have to throw away all that energy.
Static losses. And so
Right.
you have to, and this is why for higher and higher powered CPUs and GPUs, we keep dropping the operating voltage of the core, but that leads to you still have millions of transistors switching every second, and that takes a lot of current. And so you got these ultra low voltage margins,
Right.
ultra low room for error.
I know where you're going.
And extremely heavy currents on the PCB, where if you don't design your power supply traces and polygons right, you're going to, in many cases, run some sort of software and your CPU or GPU will crash because the voltage dips momentarily below the minimum core voltage.
Right.
So voltage regulation and your supply lake, your energy supply lake in the PCB itself becomes really critical. So, man, that's a big problem. If you're doing any kind of CPU or GPU, any kind of single board computer, that's your biggest challenge right there, I think.
Right.
You still have to do your, DDR length tuning, but the power supply design is, man, that can be frustrating.
Well, they did actually, some really high-level hackers at a hardware level learn that they could take chips that have supervisor modes and stuff, or an unreadable identity or something, and they play with the voltage. They take a 3-volt part and run it at like 2.2 or something, and they get it into a funny mode where now they can read the part you're not supposed to be readable. So they actually use low voltage as a hacking tool on some processor-based stuff. So here's the other thing I thought of when you were talking about these huge currents. If you have a 1-volt part and it dissipates 80 watts, like a processor, right? Those things get hot.
And you
That's
got 80
amps. Yes,
Yeah,
80
think about that.
amps
That's
at 1
crazy.
volt. It is. That's a geez.
And
My-
so it's little wonder why motherboard manufacturers quite some time ago already went to 2 mil thick copper on the
Yeah.
inner plane layers.
2 ounce or 2 mil?
Sorry, 2 ounce. Yeah, 2 mil
Okay.
would be crazy. 2 ounce.
Well, but at
Copper.
100
But
amps, it
some of
might
them are
not be
gonna
so
go-
crazy.
Some
Yeah.
of them are going to go to 4 ounce or already using 4 ounce planes.
Tell us what tell us what that is.
It's how much
4
copper
ounce.
there is.
Okay, it's math. Okay, I heard it differently. Hey,
4 ounces
what about-
of copper per square foot, I believe.
So, have you ever designed with board stabilizers? Have you ever used them, or I'm sure you've consulted on them? And
I personally have not done a PCB design that uses stabilizers. By stabilizers, you mean
the extra
bits of-
mechanical part you
bits of
solder
metal.
to it.
Yeah.
Which can
I've
also carry
serviced
some of
them.
that 80 amps too.
It can. Yeah, you can use it as a bus bar.
Yeah.
Yeah.
So, and we're used to seeing that on older stuff, but I think they're making a resurgence a little bit as the speeds go up. So
Yeah,
now,
you've got to have some good way of getting all that power where it's going
now
to go.
is a 20-layer board more stable than, say, a 4 or 6-layer board? Are you less likely to need a board stabilizer, or are you more likely because the laminations become uneven when you get real thick boards or thicker
Well,
boards?
Yeah, from what I've seen, if the fabricator is actually capable of doing more than 12 layers,
Right?
because there's a lot of factories out there that still really wouldn't go beyond, say, 16.
Yeah.
'Cause
That's
they
why I
just
put
don't
20.
have-
Yeah.
They don't have the equipment, but the ones that do have usually pretty high-end, good modern equipment and good processors. And so those high layer count boards become very stable. And usually you have a high layer count because you have a lot of plain copper in there for grounds and powers and for that kind of current. And that actually increases the stability of the board. What people have trouble with is that all that copper has to be etched to make it adhere to the adjacent dielectrics. So if you
don't
take
want
epoxy
on one side,
if you have nice polished copper, say, and you smear epoxy resin on it and let it dry, you can peel it off really easy.
Delaminate it right out. Yep.
So these boards would delaminate without that chemical etching process that oxidizes the surface of the copper and makes it rough. But then you get return path current losses because you're forcing the current through additional in the skin effect. You're forcing the current through the surface, and that's rough.
And it's following the peaks and the valleys. Yes.
Yeah. So.
Same with gridded PCBs in the old days. We try to use that to make it stick, but we were screwing up our return currents. Gridded ground planes.
That's right. Yeah. Hatched polygons.
Hatched.
Yep. So they would have better adhesion but poorer signal integrity.
Right.
So so there's no real easy way around that, and I'm kind of hoping that, because 90% of what's on your board is probably, unless you're designing a back plane, if you're just doing a normal industrial PCB design like most of us would be, only some of it is high speed, or only one portion of it is going to be RF or whatever. So I'm looking for a fab that can selectively polish or do things like that, where most of it's normal, but just that one bit that matters has been made smoother. But none of them seem to have no one's built the machines, or I'm sure there are patents. I got this idea and thought, I should patent that, and then I realized I just don't have the resources or time. But the industry needs a selective polishing process for high speed.
Oh, you looked into that a lot, didn't you? Didn't you come up with a way?
Yeah, I know technically it doesn't seem like a hard problem. It's just a mechanical CNC machine with a polishing wheel that only polishes.
That's what you said. Yeah.
That only polishes over your high-speed traces in between laminations, and would mirror that polish on the adjacent plane layers. So your return paths can be good as well, and then everywhere else you have the black oxide or the brown oxide on the copper to get good adhesion.
Right. Hey, I saw a video of yours quite a while ago, a year or so ago, and you showed the technique for if you've got 16 layers and your fab place gets them out of order, which sounds like not a big deal if you're just thinking of conductivity. But it's a real big deal if you're doing SI and transmission lines.
It's a major problem. So, traditionally designers put a layer stack indicator in the board, on the edge of the board or in their coupon, and they have the layer numbers etched into each layer, and you can tell if they're in the right order, or you can even score the side of it and polish it and look at it sideways and see where the copper is, and it should look like a stair step.
So you make layer 1 have a little bit of copper, layer 2 has more copper, 3 has more, and 4, so you can tell by the length of the copper.
You could do it that way, or just have them as
in order.
Let's say you had 4 layers, you could put a trace going off the edge of the board there, another one there, another one there, or just copper rectangles, and then when you polish the edge of the board or it's machined off, you can look at it and you can see the copper on its end on. And you can see that they're in a stair-step pattern, so they're in the correct order.
Now, running copper right to the edge of the board, though, actually violates some DRCs a lot of times.
It does normally by default, so you have to make an exception for that specific spot.
What about the PCB manufacturer? Do they complain if they're milling out copper and hitting copper, or are the tools too good?
If you make a design note in your drawings and say this is deliberate, yes, this is what I want you to build.
Yes, yeah.
Then they can't come back and say, we're not sure if you meant for this. Do you realize you've got copper coming off the edge and we're routing past that?
Right.
And unfortunately, especially if you're going to a low cost manufacturer offshore, you have to document everything like that, because they'll promise an 8-day or 12-day turnaround, and any reason to email you and ask questions gives them more time.
Right.
And they just use those things as an excuse to stall, even though it should be obvious to them just by looking at it. What you're trying to do, it should be obvious.
Right.
And any sensible person who's worked in this industry would look at what you've done and go, oh yeah, I know what you're doing there.
Right.
You
I
put that
left
on
a
the board edge, they
fiducial.
can check. Yeah.
I left a fiducial outside the board, and they did get back to me one time and said, they got back to me for this paste mask, saying, did you mean to have this outside the board's edge? And I'm like, thank you very much. No, I did not. And the DRC didn't catch it, right? Because it's not routable.
It should though, because, well, anyway.
Or Bill didn't run the DRC after he. Hey, can you tell us about fiducials real quick? We're coming up on the top of the hour, but tell us what a fiducial is on a board.
It's a dot.
It's a dot. Why is there a dot there? Well, it's there so we can line up paste masks and solder masks and the pick and place.
So you answered your own question, but a fiducial is any board feature that is used for alignment and registration alignment purposes, of the different layers of different films for the etching process, and of the actual board panels. They have fiducials.
Yes.
And it's also for pick and place machines. To the camera on the pick and place machine will examine where the fiducials are for every board that comes in on the conveyor, and it will calibrate the location and the position of the board so it places all the components accurately. So here's a very simple fiducial on this micronic keyring, that dot.
Right, I see it.
Usually fiducials have a copper dot with some solder mask clearance around them, and usually
that's what I use. Yes.
Usually they also do not allow copper to be underneath them, but really it depends on what your fabricator's asking for and your assembly house is asking for. Fiducials, I normally have them as a component in the PCB library that's not necessarily associated with any schematic symbol.
Anything, right?
It's just a standalone component that goes in the board, and I place them, and they have to be noted as
not on them.
It's also, when you're doing your PCB documentation, you should be using fiducials along with any other datums used for geometric dimensioning and tolerancing on your PCB fab drawings. So it's very clear to the manufacturers that this is a reference for everything else, you know. So
why wouldn't we use the edge of the PC board for a reference?
Because the machine that cuts out the PCBs will be all over the joint.
They're sloppy. Yeah. Yeah. So
I mean, you might be machining that and it'll be nice and smooth, but the bit can wander, and you might be excising the board by a guillotine. If it's a cheap low-cost product, you can, and some boards can be guillotined. It's kind of a brutal approach, but the more common one is V-scored. This one's been V-scored.
Okay.
So I can't get that to focus. So you see the edge of the board is not smooth, and
right.
So there's some tolerance on the board edge. So the board edge itself should never be used as a datum. You should always have some other reference, like it could just be the CAD origin in your actual layout editor.
Right. You don't have to see it for it to be an origin.
You don't have to see it, but you call it out in the drawings. There is one exception to that, and that's the theoretically perfectly flat surface. That's the table that the board is sitting on. There's an imaginary table that the PCB sits on facing up.
Right.
That is usually going to be a datum and should be a datum, because then things get compared to that, like the allowable bow and twist on the board.
Right, right. Now, there was one time, not one time, but there's an instance where we do reference the edge sometimes, and we try and do it in the drawing. And that is if there's a connector that has to line up with a housing hole or something, we'll call it out as a detail. I don't know if the PCB vendor does anything different, but what we say is, look, this has to be like 0.04 from the edge, and in a detail, because if the tolerance goes up too high compared to the edge or the standoffs, then the connector hole won't line up. So,
right.
Hey, final question for you, and then I'd ask if anybody else has questions. Tell us about a coupon. We've been talking about that before the show a little bit.
Oh, coupons. So, the coupon is meant to be a small bit of PCB that, she's smaller than this ruler, but something like this, that you ask for if you're doing impedance controlled routing or any kind of RF. You need to be able to measure what they made, not just on the boards that you designed that come out of fabrication, but you should have a test coupon on the edge of the panel that they send you, which has test traces. And there's many different kind of coupons that you can ask for and that they can build, and they're all standards based. There's a coupon standard that IPC put out, and you can
I didn't know that. Okay.
Yeah, and you can request coupons for all sorts of different things. So, for example, what people normally request is what is the obvious thing is if you have impedance controlled traces and you want to measure them with an actual TDR to see how closely the fabricator matched your specification. So if you're specifying high-speed impedance controlled nets on your board and you've got maybe 3 different impedances, you've got a differential 93 ohm for USB, you've got a 50 ohm single-ended for DDR, and maybe you have a 100 ohm differential for DDR clock and DQs, and they put a sample of those exact same trace widths and locations throughout the layer stack and the via structures you're using for your high-speed nets. They duplicate all of that on a test strip in the coupon so that they send that to you and you measure it with a TDR in your lab when you get the boards back, and you can see within what percentage they actually match your design criteria. And that's what people normally ask for coupons for. Truth is, most fabricators do very common impedance control sort of setups. So they'll have 50 ohm single-ended, they'll have 100 ohm differential, now have 93 ohm differential, I have 80, and various different things that come from other industry standards.
Various compromises, yeah.
Well, they come from standards like DDR, the JEDEC standard for DDR. And they'll have, some of them will say, well, we have our standard processors for 4 and 6 and 8 layer boards, and they have test coupons for those, which they just keep around. And if someone asks for a coupon, they send them one. Send them one, and it may not necessarily come from the panel from your production run. So if you want that, you've got to make sure you ask for it. But coupons can test other things too, like blind and buried via structures, registration. If you have a multi-layer board with stacked vias, excuse me. Or if you're doing a board that you're fanning out some 0.4 millimeter pitch BGAs, some of these things are critically important, that clearance and registration are super important. So they have specific coupons that are designed in the IPC standards that you can request and pay, and they'll send you those, and they'll section them as well, so you can look at them under a microscope.
All right.
and make sure
I'm
the
taking
VIA
notes for
structures.
next week because
Yeah.
you had talked about things like putting the BGA closer to the center of the board where the registration's better, stuff like that. But we're kind of, that'd take another hour here to talk about all that.
It would. So as always, you know, by talking, I guess we always come up with new things to talk about because there's so much, right?
We got to our first item. We had 8 items for today, and we're still on the first. But I had fun. You know, I think we talked about some good stuff too. I always learn something from you, Ben.
Yeah. Well, and likewise, I learn from you every time. And Chris, great suggestion about maybe we could do electropolishing and then laser ablate texture to prevent delamination. That's something someone needs to try that. Somehow there's always a solution. It just takes motivation and someone putting the time and effort into doing that research.
You could use something like a laser to do an interferometer to map the surface, and then you know how much to ablate. I wonder if you could use the same laser for both, right?
Yeah, possibly.
Yeah. So yeah, we'll talk about interferometers sometime. It's going on the list.
I should say next week is Black Friday and Thanksgiving. So for those of you, which is probably most, if not all, of our viewers right now live, I want to wish you all happy holidays.
Yes.
Thanksgiving,
happy holidays.
and enjoy that. Enjoy your turkey day. Bill, I don't know if you wanted to try this again next Friday or if you've got family plans.
The short answer is I don't know. So
Okay.
you want to play it by ear, or
So
do
we'll
we
play it. We'll play it by ear. We may or may not stream
That's
1 week from today, but we certainly will 2 weeks from today. Let's say that.
right. So it's a quantum effect. Until you measure it, we don't know if we're going to stream or not stream. It waits until we open the box to find out.
That's right. It's Schrodinger's day off. Schrodinger's Black Friday.
stream, right? So excellent. Good seeing you again, my friend. And we will or will not see you next week, but we will see you 2 weeks from now.
Cool. Good to see you,
Excellent.
Bill.